let's talk about the setup first, a little bit to help us understand what's going on. For those who took honors physics, this equipment might look familiar, but if not, it's good that we do a recap. So we have here a cart, and this cart is really pretty snazzy, not something we had back when I took high school physics. In the bottom is a battery pack, and connected to the battery pack then are these two little holes, which turns out are little sensors. What happens is these sensors, when they run over these strips, what are called these picket fence strips, the sensors pick up the difference and emit a signal using this light. And there's a little light source. Well, this tells you it's on, but there's another little light source in here. This little light source's infrared signal then goes to the opening there. Can you see that opening? And in that opening, then it communicates this motion encoder. How many of these strips does it go over per second? And where exactly is it located? And you can see as I move the cart, notice how that light on the sensor gets brighter or dimmer if it's slower, or just turns off completely if there's no motion. So it's pretty handy. It then connects to this device, and then you can connect this to your iPad. And this device can tell us a variety of different things. It can tell us the position. We can tap this, and instead of doing position, we can look at something else. While individual points, like what the position is at the very moment, might be helpful sometimes, what we instead really want is a graph. So on this graph, we can now see not just position, but also velocity. And if we wanted, we could even change this to acceleration. And maybe instead of position, I look at velocity. We'll do that in a moment. First, let's look at position and velocity. So in our last lab, what we did, remember, is we looked at constant velocity. So constant velocity occurs, for example, whenever I just give this a push and we assume that there is no friction. Now let's look at what the graph would look like for that. So what we'll do is we'll start the data collection, have the cart move, we'll pause the data collection, and looking at the graph, we can see the general area where we had that constant velocity, but notice that it's really hard to totally isolate friction. Right after my initial push here, we still have the influence of friction, and it's going to eventually slow down. Now what I want us to do, though, is start to look at the graphs that you made for the lab and see them in real-life scenarios. Now we're going to take a look at the first part of the lab simulation you did, where an object is speeding up in the positive direction. Now, just to point out, because you might think it's weird, the reason why the rock is on here is because this fan makes the cart start to lean over to the right, and we get a lot of friction. So this is just to balance out that added weight and prevent friction. So what we're going to do here is turn on the fan cart and with the fan, and record the position as a function of time, and then the software here calculates the velocity, and we'll look at both the position and velocity as a function of time. So let's go ahead and do that the first time here. We'll turn on the fan cart, and just to show you what it will do, the fan is directed the right way so that it pushes the cart and speeds it up. So we'll let that go while we start this piece here and take a look at the results. So here are our graphs for speeding up in the positive direction. Notice that the position versus time graph starts out with the slope near zero. That was when I was holding the cart in place, right? The position is not changing. As it speeds up, notice how the slope isn't constant but becomes steeper and steeper and steeper, and that's associated then, remember that the slope of a position versus time graph gives us the velocity value, so the velocity value is increasing, but the velocity slope remains constant, which we'll talk about in just a little bit. So right now, this is a graph of the object speeding up in the positive direction. Now let's take a look at what happens when we speed up in the negative direction. So the only way I can do that, I can't move this motion detector. Instead, what I'm going to do is go to the setup for the sensor. And first, as you'll learn when you do this a lot, the first thing we have to do is zero this quite often. And after we zero it, what I'm going to do is tell the sensor to reverse the way that it is determining position. And let me phrase that a little differently. We're flipping around our coordinate system so that this direction is no longer positive, but is negative. And we can see that as the position value becomes more and more negative, greater and greater in the negative direction. So let's go ahead and run the card again and see what the graphs look like the second time. All right, here's our set of graphs for speeding up in the negative direction. And what we want to notice is what is similar and what is different from the previous trial. The big thing that you want to be able to do with these graphs is understand the connections and what things change as a result of us, in this case, changing direction. So notice both with the last case and this case, we started with a position and a velocity just about zero. The position slope becomes steeper and steeper just in the opposite direction. And so the velocity value, the number, that speed is increasing just like before. It's just headed in the other direction. Now let's go ahead and take a look at the velocity and the acceleration graphs for these two trials. So here's the data for speeding up in the positive direction. Now we're plotting velocity and acceleration. Notice for the velocity we have a constantly increasing positive slope. And the acceleration graph is relatively constant, right? It has a slope of about 0, but the value itself is positive. And what we really want to take away is how is it that the velocity graph connects to the acceleration graph. So let's run a little bit of statistics here. So remember in the simulation what I asked you to start to think about here is what is the relationship between the velocity time graph and the acceleration time graph. So what I've done is highlighted the velocity versus time graph and taken an average slope of about 0.119. Now, the acceleration versus time graph has a little bit of wobble, and that has to do with the way the system calculates acceleration. It actually calculates acceleration using the position to find the velocity and then the velocity to find the acceleration. So there's always a little bit of wobble. So what I've done is taken the average value of that highlighted box, and the average value for the acceleration is 0.120. So notice how the acceleration value of 0.120 is just about the same as the slope of the velocity versus time graph. The slope of a velocity time versus time graph is the acceleration value. We speed up in the positive direction when the velocity has a positive value and the acceleration has a positive value. So same value, both positive, we speed up in the positive direction. Let's see if this trend continues for speeding up in the negative direction. This time we speed up in the negative direction, and so we have a negative velocity value and also have a negative slope. And so if the trend from the first part continues, we should have a negative acceleration value, which we do. Taking the mean of all of that data for the acceleration, we get a value that's about 0.11, and the slope is about 0.115 for the velocity versus time graph, both negative. So trend pretty much continues within sort of that error margin for this device. Now what we're going to do is take a look at what it means to slow down while moving in the positive direction. So what I've done here is flip the orientation of this fan around so that way it now pushes the opposite direction. Let's go ahead and take a look at that. So when I turn this on, the fan now pushes towards the detector. So to slow down, what I'm going to do is give this an initial push the other way. All right, let's look at slowing down while moving in the positive direction. First, we have to give it an initial push. And let's take a look at the data. So it's important we understand what's going on in this graph. Not all of this is slowing down. Can you identify where the pushing period of this graph for each graph is? So the pushing period of the graph is easier to show in the velocity versus time graph. Notice this area over here where the object went from a velocity of 0 to a positive greater velocity. That was when I pushed it, right? And then after I pushed it, here's where the fan opposes the motion. So notice now in a position versus time graph, when we move in the positive direction, we still have a positive slope. But the slope, instead of increasing in magnitude, and before when we sped up, notice how this slope goes to 0. As the slope goes to 0, remember that the velocity is the slope value on this graph, so the velocity also goes to 0. Now let's take a look at the acceleration versus time graph. So something important to note here. Remember what we said the acceleration is on the velocity versus time graph. The acceleration is the slope. So the slope of the velocity versus time graph is negative, just like the acceleration on average is some negative value. So slowing down means that we move in one direction, in this case positive, right? These velocity values are positive, while the slope or the acceleration is negative. So the change in velocity, the change in the vertical axis variable is opposite the sign of the variable itself. Let's take a look at this flip-flopped when we instead slow down while moving in the negative direction. So we'll do the negative direction now, and remember that to do the negative direction, I simply change the orientation of the origin and the coordinate system for this sensor. Remember that positive and negative really are just constructs. It's really important to not feel like positive has to be to the right or has to be up, but instead it's just something we flip around. So other than that, everything else is the same. I take this cart, I turn it on, and I give it an initial push. Remember I told you about balancing the weight. Don't want friction. I give it an initial push, and let's take a look at the graph for this motion. So here we are. Notice that just like slowing down in the positive direction, to slow down in the negative direction, first we have the initial push to create the motion that we have. Then the velocity, which is a negative value here, moves towards zero. So we have a slope that is positive, and that correlates with a positive value for the acceleration. But the velocity value itself is negative. So when we have one direction, in this case negative for the velocity, but the acceleration is positive, that's when we get slowing down. Let's visualize what is going on with the cart here and what it means to have velocity in one direction, but acceleration in the other direction. So what we're going to do now is talk about velocity and acceleration as vectors and how they're connected. And rather than use the carts, I'm going to use the simulation, in part because the simulation will show the vectors that we want to see. So remember we talked earlier that vectors are these quantities that have both a magnitude, a number, sort of what is the absolute value, plus a direction associated with them. So for example, when I enter into here the velocity value, and I choose it, let's say, to be 4 meters per second. Notice how the arrow points to the right. In this arrangement here, the coordinate system has been defined so that positive is to the right and negative is to the left. So if I instead enter here a value of -4, notice how that length of the arrow stays the same, but it's now to the left. If I were to change this to, say, -8, notice how the length of the arrow doubles. So the way that acceleration and velocity are related is acceleration represents a change in this velocity vector. So we're going to define things just a little bit, and we'll define them more whenever we get to the next video. But what we want for now is that velocity here, and remember that this little symbol means a vector, and I need to make note that this is not just velocity, but it is velocity average. Remember that average velocity was defined as the change in position per change in time. So what that meant is on this graph, the slope here gave us the value here. Velocity is how far do I go per some amount of time, or how far do I go on average per second. So then to define acceleration, and again we're going to make note here that this is average acceleration. We'll talk about instantaneous acceleration once we're in class together and you guys start to work through calculus. It's a very similar definition in that it is the change in velocity per change in time. So here's the big mistake that students make, and it's worth making a note to this self in your notes. Velocity average is not position over time. Do not use that, and acceleration is not velocity over time. I can't go, like, if I start at 8 and now I'm at 4 and it took a second, I can't do 4 over 1. That is a really bad strategy. It is change in velocity per some not instantaneous time interval. And so the slope of this graph then goes down here to become the acceleration value. Let's take a look at that in a little bit more detail here. So I've now set the velocity to be 0 and the acceleration to be -4 meters per second squared. So notice I have this vector here, this vector representing what is the acceleration. And I think what would then be helpful for us to do here is to define that a little bit. So when we say that the average acceleration equals -4 meters per second, what we are saying then, if we rewrite, remember that this is also the change in velocity per change in time. What we're saying is in 1 second, we are going to have a change in velocity that is equal to -4 meters per second. So whatever my start is, my end must be another -4 meters per second from that. So if I start at 0, the next second it needs to be at -4. If I started at -8, right, then going from -8 with this change in -4 should put me at -12. So to start, I start with a velocity of 0, and in this 1 second here, after 1 second, my velocity then should be at a -4. And after 2 seconds, I should be at a -8, and then at 3 seconds, which would be somewhere around here, right, I should be at a -12. So I have this constant rate of change to my velocity. Now, what this acceleration arrow represents then as well is how much my velocity vector should change. What is that change in velocity vector? And the book talks about this in the reading there. And that change in velocity vector should be the same as this acceleration vector. So for speeding up, it's all pretty straightforward, because then after a second, my velocity vector will look like that too. So let's go ahead and take a look at that with the simulation. I'm going to see if I can just scoot forward an instant in time. Well, I got rid of my settings. It's like, why is he not moving? So what we're going to do is go in here, and for speeding up in the negative direction, you can either move the guy, or you can do this. You can set a value. And then as we move through time, notice here how his velocity vector, the red arrow, is increasing in size, but the acceleration vector is remaining constant. So as we approach 2 seconds, we are at this -6 value, which, it hasn't been 2 seconds because I started at 0. Let's clear this out and just make this a little bit clearer. Reset. And we're going to put the acceleration at -4 because I don't want this to be confusing. Alright, so then we start to run through this. And notice how by the first second we're at about -4 like we plotted out, right? And then as we approach 2 seconds, notice the time's on the top left if you're wondering how I'm seeing the time. When we're at 2 seconds, we're right here at about -8. And then as we continue to move and approach this 3-second mark, we are right about at -12. So you can find what is your change in velocity if you manipulate that equation. Right, and so instead of having A equals delta V over delta T, we could write that A average. Please just get in the habit of writing average. It is so helpful. A average times delta T equals your change in velocity. So that can be a helpful tool. Now, the key takeaway I want you to see here is that when we have both the acceleration vector, in this case negative, and we had a velocity then that started at 0 but was otherwise becoming negative, we have speeding up. Whenever these signs are the same, we speed up. So we could simply reverse this if we do a reset here. And instead of having the acceleration be negative, we could make the acceleration be positive. Right? I could make this, say, +4. Maybe we make the velocity start at +1, right? So remember, that means then that the change in velocity is going to be 4 meters per second in the positive direction every second. So after 1 second, he should be moving now at a greater magnitude, right? And should now be moving instead at a value of +5. but I don't know. Yeah, something's not quite taking. But the key takeaway that I want you to have here, notice the acceleration vector isn't showing up, so something's wrong. All right, I fixed it. So now, because these directions are the same, that change from this acceleration vector makes his velocity change 2. All right, now let's look at slowing down. For slowing down, the key is that the direction of the acceleration and the direction of the velocity are opposite. Let's talk a little bit using that equation why this is the case, just making sure that conceptually we understand this. So if the velocity vector right now looks like this, and it is negative 12 meters per second, remember that the acceleration is defined as what is the change in velocity per some amount of time. So if this is positive 3 meters per second squared, what that means is in 1 second we have a change in velocity that is equal to positive 3. So if change in is defined as v final minus v initial, and v initial is negative 12, then we have that this v final minus a negative 12 should equal 3. And so minus a negative makes a positive, right? So we have v final plus 9, or excuse me, plus 12 equals 3. And so when I subtract the 12 from both sides, we have that v final has now changed to a negative 9 meters per second. That magnitude has decreased, and so if this is the 0th second, then after 1 second, we now would have a vector. I'm going to draw the 12. This is what it originally was, right? And we have subtracted, we have removed that acceleration piece from it so that I now have a velocity at 1 second that is smaller than my velocity at 0 seconds. I am slowing down. And this is helpful to point out, do not ever use the word deceleration, please. It is a term that people use when they don't really understand physics and they just are trying to refer to the fact that something slows down. When we say deceleration, what we really mean is that acceleration and velocity have opposite signs because they are in the opposite direction. Things slow down when they are in opposite directions. Things change direction whenever A and V are not fully in the same direction. So like when you turn your car, right? If you're moving like this and you turn your steering wheel a little bit to the right, you start to move in a curved path, but not necessarily slowing down. And we'll talk about that later in the year. For now, we're just talking about left-right one-dimensional motion, and so if my velocity is to the right but my acceleration is to the left, then I slow down. Or if my velocity is to the left and my acceleration is to the right, I slow down until I come to a stop. So that's what we see here in this simulation, right? If we run this, to start, the guy comes to a stop, right? That's right here where we're at the x-intercept on the velocity time graph. It took 4 seconds because 3 times 4 equals a positive 12, and that's when we have positive 12 plus negative 12 makes us at 0. And then we start to speed up in the other direction, and out comes the man flying back in the other direction. Speeding up because we have a positive acceleration and a positive velocity. All right, so hopefully that helps to visualize what I'm talking about with the carts. And when we have the fan opposing the motion or pushing and providing acceleration in the same direction as the motion. Now, because the fan cart is always pushing, what we can do is have the fan cart move so that the fan slows it down. And then what happens the instant after it comes to a stop? It then will speed up in the other direction. So let's do that and track the motion of the cart for that slowing down and then speeding up. Let's take a look at the graph. So here's the graph for the cart moving in the negative direction to start while slowing down and then speeding up in the positive direction. This is the sort of graph that you need to be able to understand and identify where we have each type of motion. For example, you should be able to identify when did the cart come to a stop. That occurs right here at the x-intercept. But notice that the acceleration never goes to 0. For it to go to zero would mean that we'd have to have a velocity of zero for more than just an instant in time. Otherwise, the slope of this remains constant the whole time. Notice how the slope the whole time is positive. So while the velocity value is negative, with a positive slope, we slow down. The moment after we stop, though, the cart starts to move in the positive direction, and so a positive slope or a positive acceleration combined with a positive velocity value for the direction of motion means that the cart speeds up.